Picture yourself driving toward a city. At every junction, your map app flashes a number. About 40 kilometers to go. You know three things about that number. It is only an estimate. It keeps changing as you drive. And crucially, it never claims you are closer than you truly are. It might say 40 when the honest truth is 45. It would never say 30. That guiding number, the distance still to travel, is a heuristic. And this one-sided honesty, never overshooting the truth, has a name, an admissible heuristic. Get it right, and clever search finds the genuinely cheapest path. Let's see exactly why. First, the vocabulary. Four quantities that run every informed search. We're moving through a graph of states, from a start toward a goal, and each edge from n to n prime carries a step cost. C. G of n is the cost you have already spent getting from the start to n, the road behind you. H of n is your heuristic, an estimate of the cost still ahead, from n onward to the goal. It's the guess. And H star of n is the truth you're estimating, the actual cheapest cost from n to the goal, if you could see it perfectly. The whole game is H guessing at H star. Informed search scores each node by adding two of these, the cost behind plus the estimate ahead. That total is f of n, g plus h. It's the algorithm's hunch about the best full path running through n. One convention we lock in now and lean on all lesson. At any goal, there is nothing left to travel. So h of the goal is 0. Here is a little map. Start at S, reach the goal G, and every road shows its cost. The obvious idea. At each step, just walk toward whatever node the heuristic says is closest to the goal. That's greedy best first search. Always chase the smallest h. Suppose our heuristic hands us these estimates, the little blue h values. Look at SS to neighbors. A guesses 3 to the goal. B guesses 4. Greedy only reads H, so A looks closer. Off it goes to A. From a, the goal itself has H0 smaller than anything. So Greedy commits to the road A to G. But look at that road's cost, 9. Greedy just spent 2 plus 9, 11 to reach the goal. Now watch the path Greedy ignored. Go S, B, C, G. Instead, 3 plus 2 plus 2. That's only 7. Greedy was led straight into a dead-end road by a tempting-looking guess. It is fast, but it is not optimal. So what separates a heuristic that helps from one that hurts? Exactly this. A heuristic is admissible when, at every single node, its guess h is at most the true remaining cost h star. It never overestimates. It's fine to underestimate. Even guessing 0 everywhere is admissible, since 0 is never bigger than a non-negative cost. That case just gives you no guidance at all, and the search plods. The art is guessing as high as you dare, without ever crossing the true cost. Let's test it on our map. First, the truth. The real cheapest cost from each node to the goal, H star, in green. From C it's 2, from B it's 4, from R, the only road out costs 9, and from S, the best route totals 7. Now overlay our heuristic and check each node. S6, at most 7, good. A3, at most 9, good. B4, at most 4. Right on the line, still allowed. C2, at most 2, fine. And the goal, 0 equals 0. Every node passes. This heuristic is admissible. And that is the exact property that will let A star, next lesson, guarantee the truly optimal path. Now, what if one guess had overshot? Say the guess at A had been 7, while the true cost is only 5. 7 is bigger than 5. The heuristic overestimates at A. That single overshoot is enough to break admissibility, and it can make A star return a path that is not the cheapest. One red node poisons the guarantee. There's a stronger, tidier cousin of admissibility called consistency or monotonicity. It asks something about every single edge. Take a step from n to n prime, costing c. Then the estimate at n must be at most that one step plus the estimate at n prime. It's just the triangle inequality. Going straight from n toward the goal can't be dearer than detouring through n prime first. The guess is not allowed to drop faster than the road actually falls. And here's the payoff. Walk along an optimal path to the goal and write consistency on every edge. At the very last node, the goal, h is 0. Add all those inequalities and the intermediate h's cancel. Telescoping down. What survives is h at the start. At most, the total cost along the path, which is exactly h star. So every consistent heuristic is automatically admissible. The reverse, though, is not true. A heuristic can be admissible yet still break the triangle inequality on some edge. Admissible, but inconsistent. Keep that gap in mind. It's a favorite trap. And when your heuristic is consistent, S star never has to revisit a node it already settled. Let's make all of this concrete with real numbers. A small directed map, start S, goal G, and two ways round through A or B. S to A costs 2, A to G costs 5, S to B costs 4, B to G costs 3. First find the truth. H star at each node. G is 0. From A, the only road is 5. From B, 3. And from S, the cheaper of 2 plus 5 or 4 plus 3. Both happen to be 7. So H star at S is 7. Now test a candidate heuristic. H of S is 6, A is 5, B is 2, G is 0. Admissibility asks H at most H star at every node. 0 at most 0, 5 at most 5, 2 at most 3, 6 at most 7. Every line holds. So this heuristic is admissible. Consistency is stricter. Test every edge, h of n, at most the step cost plus h of n prime. S to A, 6 at most 2 plus 5, 7. S to B, 6 at most 4 plus 2, 6 tight, but it holds. A to G, 5 at most 5. B to G, 2 at most 3. All four hold. So this heuristic is not only admissible, it is fully consistent. The best kind. And watch how that heuristic steers the search. Esther scores each node by fg plus h. From S, f is 6. Expand it. A gets f of 7, B gets f of 6. B scores lower, so it goes first. Expanding B reaches the goal with cost 7. And 7 is exactly h star at S, the true optimum. Because the heuristic never lied, A star found the genuinely cheapest path. That is the whole reward for admissibility. One last idea, and a practical one. Among admissible heuristics, some are better than others. If one heuristic is at least as large as another at every node, while both stay honest, we say the bigger one dominates, and a bigger admissible heuristic expands fewer nodes. It's more informed. Take the 8 puzzle. Slide tiles into order. Here's a scrambled board on the left, the goal on the right. Every move slides one tile, costing 1. Two classic admissible heuristics estimate the moves still needed. The first just counts misplaced tiles. How many are not yet home? 6 of them are out of place. It's admissible because each wrong tile needs at least one move. The second, Manhattan distance, sums how far each tile must travel. It's rows plus columns away from home. Add those up, and you get 9. It's admissible too, since a tile can't reach home in fewer steps than that distance. Both are honest, but 9 beats 6. Manhattan dominates counting misplaced tiles. It always gives the larger, sharper estimate, so S star guided by Manhattan explores far fewer nodes to reach the same optimal answer. When you can, pick the largest admissible heuristic you can find. Your turn. Here's a fresh graph. S to A costs 1, A to G costs 1, and a direct S to G costs 4. Someone proposes this heuristic h of S is 2, A is 0. G is 0. Two questions. Is it admissible? Is it consistent? Pause, work it out. Then check yourself against me. Here's the reveal. First, the truth. From S, the cheaper route is 1 plus 1, 2. So H star at S is 2, at A it's 1. For admissibility, S2 at most 2, A 0 at most 0. All fine. So yes, this heuristic is admissible. But now consistency. Check the very first edge. S2A is H of S 2 at most. The step cost 1 plus H of A 0. That's 2 at most 1, which is false. The heuristic drops too steeply across that edge. So it is admissible but not consistent. The exact gap we warned about. If you spotted that, you've truly got it. Trap 1. Thinking the heuristic must be exact. It doesn't. It only has to avoid overestimating. Underestimating is perfectly fine. It's the whole point. Trap 2. The dangerous one. Overestimating even at a single node breaks admissibility, and S star can then return a path that isn't the cheapest. Overshoot is the failure mode, not undershoot. Trap 3. The direction of the arrow. Consistent always implies admissible. The reverse fails. You can be admissible yet inconsistent. Exactly as our practice problem showed. Trap 4. Greedy best first. Chasing only the smallest h is fast but not optimal. Remember, it marched into that 9-cost road. You need F, G plus H for a real guarantee. And trap 5. Small but essential. The heuristic must be 0 at the goal. Every proof, including consistent implies admissible, leans on it. Drop it, and everything wobbles. Let's bring it home. A heuristic is just a cheap estimate of the cost still to go, from a node to the goal. Domain knowledge that steers the search. It's admissible when it never overestimates the true remaining cost. H at most H star everywhere. That one-sided honesty is what lets A star return the genuinely optimal path. It's consistent when it obeys a triangle inequality on every edge. And consistency always implies admissibility, though not the other way round. Greedy search, chasing the smallest H alone, is quick but can be fooled. So real optimality needs F, the cost behind plus the estimate ahead. And among honest heuristics, the larger one dominates and searches less, like Manhattan distance beating a simple count of misplaced tiles. Hold on to these. And next lesson, A star will fall straight into place.